starting with the anterior pituitary. Again, we go from the hypothalamus releasing hormones as well as inhibiting hormones. So the hormones that are being secreted by the hypothalamus. Let me close it. So the hypothalamus that's releasing these releasing hormones as well as the inhibiting hormones are targeting the anterior pituitary. And we know those hormones are traveling through the portal system, the hypophyseal portal system that connects the capillary bed surrounding the hypothalamus as well as the capillary bed surrounding the anterior pituitary. There's this one narrow highway, which is called a portal vein, that will drain across, and that allows communication between, or rather communication downstream from the hypothalamus to the anterior pituitary. Now those releasing hormones target these 5 somatotrophs, or rather the trophic cells. These are the cells that are located in the anterior pituitary that produce 7 types of hormones. We have our somatotrophs that produce our growth hormone, thyrotrophs that produce our thyroid stimulating hormone, gonadotrophs producing our FSH and LH, lactotrophs producing prolactin, and our corticotrophs that are going to be producing our ACTH and MSH. And I'll talk about each of these 7. The ones that we did talk about that target tissues directly. So now we're going from the anterior pituitary out to the target endocrine organs or the tissues. Human growth hormone targets bone and skeletal muscle mass. We have our prolactin that targets our mammary glands, and our MSH, our melanocyte stimulating hormone, that targets the melanocytes in the skin as well as the hair and any areas that we do display any pigmentation. And so when we talked about at the tail end of Tuesday, is we highlighted 3 of the hormones on this table that need negative feedback, to provide negative feedback from the target tissues back to the hypothalamus, because the hypothalamus are going to have receptors that are going to be attuned to some inhibiting hormone of some kind that limits the production of that growth, or I'm sorry, that releasing hormone that targets the anterior pituitary. So think of it this way. Hypothalamus releases growth hormone releasing hormone, which is going to target the somatotrophs. Again, the somatotrophs being the cells in the anterior pituitary. Now, when growth hormone releasing hormone targets these cells in turn produce human growth hormone. So now somehow we have the production of human growth hormone, and we don't want too much of it depending on where we are in terms of growth. We want to be able to take that growth hormone to come in and turn off the production of growth hormone releasing hormone. So whatever starts the production of it, you also want to turn it off. And that's being a running theme that we're going to be able to see in the remainder of this lecture. And so the growth hormone inhibiting hormone that we're going to be able to see that comes back in, GHIH, not GHIT. GHIH is growth hormone inhibiting hormone. And that was produced, when we look at our growth hormone inhibiting hormone, is somatostatin. That is something that's going to be produced by other organs. And those are, you'll see, are produced in the intestines. We produce them in the pancreas. This is feedback in the digestive system that comes back and turns off the production of human growth hormone. Why the intestines and pancreas? Because if you think human growth hormone, let's not forget the other function of human growth hormone, which is all related to metabolism. So something that's related to metabolism. We've got enough glucose. I don't need to free up glucose from the liver. I don't need to free up lipids from our fat tissue. We've got enough energy. Let's go back and turn off the production of human growth hormone so that we don't release that much more energy. We only release what we need to get what we need, and then we come back from the very beginning, back at the hypothalamus to say, limit that production, we're good. Okay? So we mentioned this growth hormone inhibiting hormone. Oh, well, I'm looking at the wrong one. growth hormone inhibiting hormone. I mentioned the same thing with prolactin. Prolactin releasing hormone targeting the lactotropes in the anterior pituitary, resulting in the production of prolactin, which targets the mammary glands. And then we're going to be able to see prolactin inhibiting hormone, PIH, being dopamine. And dopamine secretes back into, there's receptors on the hypothalamus that have receptors for dopamine. And when dopamine attaches, it's going to inhibit the production of prolactin releasing hormone. So all of this is that negative feedback. And the same thing with MSH. Or MSH, we have another inhibiting hormone that will come back and limit the production back there. All the rest that we're going to be looking at, we'll be looking at thyrotropin releasing hormone. We'll be looking at gonadotropic releasing hormone for both FSH and LH. We'll be looking at corticotropin releasing hormone, where we have adrenocorticotropic hormone, as well as, just that last one. These are the hormones that are going to target. We're going from the anterior pituitary to the next target, peripheral endocrine organs. So let's take a look, starting now that we have that pathway. We'll start looking at our peripheral endocrine gland. Before I start, what questions do we have about anything we covered on Tuesday?
So just those three that you highlighted work with negative feedback?
Yes.
And the rest and the others are?
You're going to be able to see what's going to be the negative feedback. The negative feedback is going to be provided by the hormones produced by the peripheral endocrine organs.
But the other ones, do they use a positive feedback?
No. This is all negative feedback. So if the brain down the line is producing a hormone, you want to be able to turn off the production of that hormone. That's all it comes down to. And you'll be able to see the first thing we're going to be talking about is thyroid hormones, which is all related to boosting our metabolism. We want to be able to turn that back off, back where we started. Okay, so that's the whole concept of negative feedback. What lends itself to the production of turns it back off. This is our way to limit the amount of that hormone. Any other questions? All right, so let's look at the hypothalamus pituitary thyroid axis. So where we're specifically working from, hypothalamus to the pituitary to the thyroids. This is one of the common axes that you'll see that's in charge for metabolism. And so as I described on Tuesday, the hypothalamus is going to produce a thyrotropin releasing hormone, TRH. And the thyrotropins, where are the thyrotropes? The thyrotropes are the cells located in the anterior pituitary. So naturally, these hormones, this hormone is going to come in and stimulate the thyrotropes to produce the next hormone in line, our thyroid stimulating hormone. And obviously, just looking at the name, thyroid stimulating hormone, otherwise known as TSH, is going to stimulate the thyroids. So once that hormone makes its way into the circulatory system, it's going to find an area that is going to have receptors for TSH. And where are they located? Specifically on the thyroid. And that thyroid is going to then produce another hormone, which are going to be our thyronine molecules. And you'll be able to see what that looks like on the next couple slides. The thyroid stimulating hormone, again, produced by the anterior pituitary, does exactly that. It's going to stimulate the thyroid for the production of T3 and T4. These are the big two hormones. And again, as I mentioned, tri meaning 3, iodo meaning iodine, and thyrronine being sort of the base molecule. That's the molecule, the lipid-soluble molecule that you'll be able to see that our iodines are attached to. And tetra being 4, iodo being iodine again, T3 and T4, of which the bulk that's being made by the thyroid is T4. And now that we have the thyroid, our thyroid producing T3 and T4, what's going to come back is a form of negative feedback. T3 and T4, when we make enough of it, is going to go back and turn off the production of our thyrotropin releasing hormone. It will go back to the hypothalamus and say, I've got enough of this, limit that production. Okay? So looking again, as I mentioned, the hypothalamus will have receptors for it saying, if I've got enough, I can turn off. And what it's going to stop doing is producing thyrotropin-releasing hormone, which in turn will limit the amount of thyroid-stimulating hormone, which again will, in turn, limit the production of our T3 and T4. So that concept you should get by now. Let's take a look at our next slide. What exactly is a thyroid? Again, right in front of the throat. I'm not going to spend too much time on the anatomy, but for the most part, there is a rich blood supply around the thyroids due to what that thyroid is responsible for. As I mentioned, it's tied into metabolism. We'll look into the functions in just a bit. Now, the thyroid gland, if we were to go zoom in right into the thyroid itself and look at the functional unit of the thyroid, we're going to have thyroid follicles. And zooming in, you can see our cuboidal epithelial follicular cells that surround this pool called thyroglobulin. And it's this gel matrix. It's this glycoprotein pool in which we turn TGB, which is our pool of thyroid hormone precursors, that can get transformed into T3, T4. So this is our backup supply, of which we have about 100 days worth of T3 and T4 that we can produce to regulate our metabolism. And surrounding it, like I said, are follicular cells surrounding the area, and in between we have parafollicular cells that are riddled in between these follicular cells. I'll talk about these, but these are going to be related to calcium regulation. Right now our focus is on the follicular cells that are responsible for the production of T3, T4. They'll be producing T3, T4. The storage is this gel right in between. Those thyroid functions, take a look at the different thyroid functions. The first term you're going to see on there is our basal metabolic rate. And our basal metabolic rate is exactly that. It's your measurement of your metabolism. How many calories are you burning in a day to maintain your bodily functions? And how do you actually measure your basal metabolic rate? That's you literally laying down, eyes closed, and doing minimal. I mean, literally not even thinking. It's just you sitting there and being able to maintain the energy requirements to simply exist, just to maintain your tissues, to keep your neurons firing when they need to, anything that requires ATP. So all this is going to be related to how much ATP we produce. At times we start to ramp up a little bit more, right? If we're involved in any physical activity of any kind, we're going to start to boost our metabolism. If you're sitting here thinking during the test, well, hopefully you're thinking during the test, but you're taking the test and your brain is churning out, you're going to start to up your metabolism. So your thyroid hormones will be working to raise your metabolic rate to match what your metabolic demands are. Thermogenesis is the generation of heat. At times when you're cold, we need to up your metabolism to start generating heat. And as I mentioned before in our earliest lecture, this is going to employ the second law of thermodynamics, in which whatever energy you burn, a good percentage of that will be converted to heat. And that heat is used to maintain our body temperature at 98.6 degrees. Now, if it's colder outside, just like it is today, you're probably going to start to shiver more. And that shivering is all related to being able to raise heat. You start getting a lot more muscle action going on. You have your muscles slightly contracting, and your metabolism increases to be able to raise enough heat to keep you at that temperature. So all that is related to your metabolism. And you can start to imagine that any imbalance in your thyroid hormones will start to affect your metabolic rate, will affect how fast you're burning energy. It will affect your energy levels. Are you feeling weak? It'll also affect your temperature. How do you feel cold? Do you feel hot, etc.? Now, the thyroid hormones, when looking at our metabolism, we break that down into the three major components for our energy sources: proteins, fats, and carbohydrates. We've discussed carbohydrate metabolism. That is our burning of glucose and how it enters cellular respiration. We've talked a little bit about how fats can get broken down into fatty acids to enter the Krebs cycle. The next thing we talk about is protein. Now, we don't want to use protein as a viable energy source initially because those proteins are going to be used for the production of proteins. We turn those proteins back down to amino acids, and those will get used for anything else. Thyroid hormones also are going to have, they can help regulate the effects of epinephrine. So any sympathetic activity or any sympathetic dominance that takes place, our thyroid hormones will come in and intervene and work together. Thyroid hormones also have a synergistic relationship with these other molecules. HGH, remember, human growth hormone wants to be able to produce energy for us. So we're going to increase glucose usage. We're going to increase the use of fats. So all of these naturally, thyroid hormones will work together with human growth hormone, insulin for being able to store energy, and then looking at times at which thyroid hormones are heavily involved in growth. So think about the times when, especially during times of puberty, we're going to start to ramp up the metabolism by utilizing these hormones, human growth hormone and insulin, which are both anabolic hormones. Human growth hormone builds things. Insulin builds larger molecules like glycogen. They're going to be involved in building. So combine that with our thyroid hormones, we're going to start to increase our metabolic rate utilizing fat and carbohydrates to start building these big macromolecules so that in the purpose of growing our skeletal system as well as those nerve pathways. Hence, that's why this is an important concept of why not just at birth, but during childhood, they want to make sure that you have enough thyroid hormones. Because due to any lack of thyroid hormones, especially at a younger age, can end up stunting your growth. Yes?
So that I have my 10-year-old's going to have a stim test done at Children's Hospital.
A what test?
Stim test to check for growth hormones. If they're giving her a blood pressure medication and then stimulating her pituitary gland, is that also to do with thyroid?
It depends what they're measuring. If they're measuring growth hormone, what they're looking specifically is for growth hormone. Now they can derive thyroid function by just doing blood tests, looking up at T3, T4, and then they can measure TSH. And if they don't see any problem with the thyroid metabolism, that's where the other component comes in. T3 and T4 work synergistically together with HGH. So combine HGH, T3, and T4. If T3 and T4 levels are normal, but HGH levels are low, well, then we kind of know where the culprit is. And what they could do at that point is they can give children that are a little bit slower in the development stage, at least physically, they can give them human growth hormone to kind of speed it up a little bit. I've seen that in cases, actually technically just seen it with cases with friends where they've had younger brothers and sisters that get prescribed human growth hormone. And that's just to keep them up physically. And it's kind of funny to see, and I know this is kind of just an anecdotal cases, but the child that I remember seeing that was on growth hormone all of a sudden started having huge growth spurts, because that's what they've been missing. Metabolism is fine due to T3 and T4. We know those levels are fine for upping their metabolism, but they need that other component that's going to help stimulate growth. All three of these, our thyroid hormones, human growth hormone, and insulin, all these anabolics need to work together to really amp up growth at that point in time.
So do type 1 diabetics, because I would be surprised, do kids have that? Do they have a trouble with growing?
If they notice that growth patterns are not as fast as they should be, it's another thing that they'll look at too. So the fact that they do not produce, especially type 1 diabetics, that cannot naturally produce insulin, and that's because their own immune system starts attacking their pancreatic cells, they can no longer produce insulin. So again, thyroid hormones are fine, human growth hormone levels are fine, but they need to get insulin, so they may get insulin, well they do get insulin, and they may actually get additional growth hormone with it too. Something that they typically do. It's a balance of all of those, especially during that time that's needed. Question?
What's the difference between T4 and T4-free?
Oh, we'll see that in the next slide. I'm just talking about just the thyroid hormones for now. Okay, well now I can describe the difference between T3 and T4. So the hormones that are released from our thyroglobulin again, that pool right in the very center, is going to produce T4. That's the main hormone that's produced out of TGB. And again, if you look at the structure of T4, 4 iodine molecules are thyronine. The other name for this, for T4, is thyroxine. So I know I mentioned T4. Where is T3 coming in? Our thyroid can also produce T3, but down the line where the bulk of it is produced is actually produced in, oh gosh, where is it produced? I totally blanked out on where that's produced. I'll remember in just a little bit. So we produce these elsewhere, but what starts it all off is the production of T4. Now the thing about the T3 is that it's much more active. We produce more T4, but T3 is the most active thyroid molecule, okay, thyroid hormone. And so you'll see that conversion taking place in the blood. And in this slide, what you can see, and I'm not going to have you guys memorize the slide. What I just want you guys to get from here is to take a look at our thyroglobulin, which is this pool right here in the center. This is all TGB. These are the follicular cells surrounding, again, the cuboidal epithelial cells surrounding that colloid mixture of TGB. And you can see in this process how T3 and T4 is produced. So what's taking place is the thyroglobulin is produced in these follicular cells. They come back out, they're packaged up in the Golgi apparatus, and they get secreted out into that whole pool of TGB. So the follicular cells are producing it. Once TGB is in here, we are importing iodine from the circulatory system. Now the question is, where does iodine come from? Well, this is where naturally we can get iodine from our diet, okay? But I don't think it's a trace element, but it is just a little bit of iodine that we need in order to produce, in order to get iodine into our bloodstream. So we extract it from our diet. That comes in and makes its way. Once it's flowing through the circulatory system, it makes its way into the follicular cells, and then makes its way out into, it's exocytosed into, actually I'm sorry, not exocytosed, it's channeled out into the TGB, where TGB mixes with the thyroglobulin and will start to bind onto areas of that thyronin molecule. Once it's assembled T3, T4, then it is phagocytosed. I'm sorry, not phagocytosed, but endocytosed. It's taken into the cell. We're going to see the cell now taking in T3, T4. Lysosomes are going to come in and basically cleave some of the things on there just to cut off some of the excess. And then T3 and T4 are going to be back into, it's going to get transported back into the blood. So this is our way of taking an iodine, making T3, T4, and right back out. And if you go back to that earlier slide on Tuesday, you'll see the structure of our thyronin molecules and where iodine attaches. That's exactly what these enzymes are involved in producing it. Now that T3 and T4 makes its way in, once it makes T3 and T4 makes its way in, T4 gets converted into T3, and a lot of that takes place in many areas of the body. I believe the liver was one of them. Muscle also makes it, and areas that are going to be involved in metabolism. So now we have T3 and T4 floating around, but keep in mind that these are lipid-soluble hormones, so they're going to require albumin. It's a specific carrier that's similar to albumin. It's called the thyroid-binding globulin that will come in and attach to allow those to be dissolved in blood. So as I mentioned, T3 is the active form, and even though I did mention it's heavily involved in growth of the brain as well as the skeletal system, it's something that they typically would test, especially upon birth of a child, since that period of birth up to late childhood is important for development. So one of the things that they do for testing newborns is they do a TSH prick. Basically what they're doing is they prick the heel they're wanting to determine the amount of TSH as well as T3 and T4 in their blood. And if they can determine that those are normal levels, they know that the metabolism will be fine. They know if TSH levels are low or T3 and T4 levels are low, they can diagnose it at birth to make sure that their metabolism stays normal. They can give them certain drugs, they can monitor them, and make sure that their development is not stunted from that point on. So the way they can diagnose hypothyroidism as well as hyperthyroidism, either too low or too high of these molecules, is through the measurement of T4 levels, T4 being thyroxine. So now that we have that in place, let's take a look at the feedback that takes place to limit the amount of T3 and T4. So we don't want too much of it, and we don't want too little of it. In order to keep it within that window, we need to employ negative feedback. So here, this is going to describe everything that I've already described, in which our thyrotropin-releasing hormone is produced by the hypothalamus. TRH makes its way down the portal vein into the thyrotropes in the anterior pituitary, which produce TSH. TSH is secreted out into the circulatory system, which makes its way over to the follicular cells. The TSH then stimulates the follicular cells to start producing T3 and T4. That T3, T4 then makes its way out to the circulatory system and makes its way back where it can come back and turn off the production of thyroid-stimulating hormone and turn off production of thyrotropin-releasing hormone. So the production of T3, T4 in the efferent pathway will turn off the production. So by turning it off, we limit the amount of T3 and T4 that's made in the first place. The next slide over basically shows the same thing. T3 and T4, TSH, T3 and T4 coming back in and turning off TSH and TRH. Now, when T3 and T4 are low, right? So then again, looking at, let me just draw the receptors over here. And this is a receptor for thyroxine, or T4. If there's not enough T4 in our blood, that will come back in and if we have less T4, we have less receptors that will stop the production of TRH. Meaning, the lower amounts of T4 in the blood, low T4, will stimulate the production of TRH, which will then make TSH, which will then make T3 and T4 to raise them back up. And when that's back up, that T3 and T4 will come in, bind to these receptors, and block the production of TRH. So by now you should see this pathway that leads itself to inhibition down the line. So other things that I can point out for our thyroid hormones, things that I haven't already mentioned: increase of body temperature, the stimulating protein synthesis, so we do want to make sure that this is protein sparing. Increase the use of glucose and fatty acids. So out of all the things that we looked at, protein, fat, and carbohydrates, we want to rely, our thyroid hormones will allow us to use carbohydrates and use fats as a metabolic substrate, things to undergo cellular respiration to produce ATP. But we want to limit the amount of protein being metabolized to produce ATP. So this is what we want to do. So T3 and T4 are going to have receptors located in the liver, in the muscle. You're going to see receptors in adipocytes, fat cells. You will see areas that are involved in the production of catecholamines, mainly our epinephrine. You're going to see the synergistic effect that I mentioned with growth hormone as well as insulin, all for the purposes of anabolic reactions to promote the growth and building of macromolecules. Now that we've kind of explored that concept and gone over and over, let's sort of take a look at disorders that are related to imbalances in thyroid hormones. And the first of these is a phenomenon called goiter, which is the enlargement of the thyroid gland. Any goiter, G-O-I-T-E-R, anytime the thyroid is not working the way it should be, whether it's producing whether it's overly stimulated or it's constantly producing thyroid hormones, is going to cause an enlargement of the thyroid gland. And looking at the process, as we mentioned earlier, going back to the production of T3 and T4. The production of T3 and T4 wholly requires the presence of iodine. And going back to that earlier slide, if there's no iodine going in, we're not producing T3 and T4, right? Because we just can't produce it, because that's what T3 and T4 read. They require iodine in their production. So what's happening specifically with that production, with the lack of production of T3 and T4? T3 and T4 cannot go back and turn off the production of thyrotropin-releasing hormone. So now that we can't turn it off, our hypothalamus is constantly producing TRH, which is going to go in and stimulate the thyrotropes in our anterior pituitary, which is going to further produce more TSH. And that TSH is going to constantly come in and stimulate that thyroid to keep producing, to try and get it to produce T3 and T4. So this overstimulation due to that excess of TSH is all due to the lack of iodine. And this is something that they look at, especially in third world countries. They noticed that the people in third world countries were having a lot of symptoms related to hyper and hypothyroidism. And what they found out, and literally is just looking at diets, looking at everything else, they realized that the thing that they were missing was iodine. And so we had companies, and they realized this was actually something that, I forget which global entity it was, realized that the introduction of iodine into something as simple as iodized salt, well actually salt, and add iodine to it costs like a fraction of a cent, just for somebody to have that much iodine. So if they introduce it into salt, and people eating iodized salt would come in and bring their metabolism back to normal, as long as that iodine can produce T3 and T4, it can come back and turn off the production of TRH, which will limit the production of TSH, and therefore maintain regular thyroid function. So with that, we saw reducing the incidence of goiter and a better quality of life. So let's sort of take a look at hyperthyroidism. And the most common one is called Graves' disease. And this Graves' disease is actually more common in females. You get more of it. About 2% of the female population have some form of Graves' disease, in which 5 times more women are affected by Graves' disease than men. There is a genetic component behind it. Most cases of hyperthyroidism, about 50 to about 80% of those are due to Graves' disease. So if anybody has a overly, at least a clinically hyperactive metabolism, it's due to that. So what symptoms do they typically experience? Imagine a metabolism ramped up. Someone constantly feels weak because whatever they eat is devoted to maintaining that metabolism. They're constantly burning calories. Therefore, they need to eat, and they cannot get enough of it. In fact, their heart rate is overly high. So tachycardia is elevated heart rate. Goiter. Looking at goiter is, again, their thyroid that's constantly working overtime. So hyperactivity, hyperthyroidism. And something that I can't necessarily explain because I haven't really looked too much into it is bulging eyes. If you ever look at anybody with Graves' disease, their eyes just bulge out, and I haven't quite looked into why. So let's take a look at the etiology of the disease. What causes Graves' disease? It's an autoimmune disorder that comes in and where an antibody, our own antibodies, come in and mimic thyroid stimulating hormone. So T3 and T4 make their way back in. They can produce T3 and T4 just fine. That comes in and can turn off TRH, turn off TSH, right? And that will limit the production of T3 and T4. However, we have their own antibodies come in, and this one specifically is an immunoglobulin. You don't need to know that. But that will come in and bind to the TSH receptor. Yeah, it will bind to the TSH receptor on here, stimulating more of a production of T3 and T4. So T3 and T4 can still turn off, but you've got something that mimics TSH and still binds to it. So any way you look at it, even though we still have negative feedback on the anterior pituitary, our immune system is still attaching or attacking that thyroid. So give that thyroid, get that kind of thyroid to constantly work. That the gland will start to grow bigger and bigger and continually churn out T3 and T4. And therefore their metabolism goes up, their body temperature goes up, they constantly feel weak. You look at them and their metabolism is heavily ramped up. They constantly have the effect of the catecholamines working on, it's that constant sympathetic drive that they have depending on the severity of it. Those are your common symptoms. You also see a lot of muscle wasting taking place. You see a lot of fatigue, weight loss, high blood pressure. All in all, it's an overly active metabolism.
But it binds to it directly, right?
It binds to the TSH receptor in the thyroid.
Yeah, but as you said, can you go back to
Yeah, of course.
So you said that although the TRH is turned off,
Yeah,
something mimicking turns on,
yeah.
but directly in that site?
Directly on the thyroid follicles. So now if you were to measure somebody that has Graves' disease, their TSH levels would be low. And that should make sense because they've got enough T3 and T4. So the hormones produced by the hypothalamus turn off the production of TSH, but then the immune system comes in and starts binding to the TSH receptors. So what you would expect clinically, if you were to do a blood test on them, low TSH, you find very high T3 and T4, and obviously the rest of the symptoms involved. And so what they could do is they could look up, and I don't know the treatment for it, but they can find what ways could they turn off the thyroid. And I haven't really looked too much into it, but they have ways of being able to diagnose it. There's endocrinologists that are specializing in this type of stuff that want to make sure that we get normal endocrine function of the thyroid. So that's hyperthyroidism. Let's take a look at hypothyroidism. Again, if hyperthyroidism was an overactive metabolism, hypothyroidism would be a slow metabolism, a clinically slow metabolism. So in this process, hypothyroidism is reduced production of TSH as well as thyroid hormones. We just simply cannot produce enough T3 and T4. Despite having low counts of TSH. So there's different reasons for them. But when you look at the population that's at risk, it's mostly women over the age of 60. Okay? This may explain when you start to see the slower metabolism. Okay? Typically, things that you would see with a slow metabolism is a low metabolic rate. I mentioned that T3 and T4 is related to thermogenesis, has a direct effect on how much heat you can generate. So if you got low thyroid counts, you expect to have really cold skin. Dry skin, very weak, because you can't ramp your metabolism up. You feel cold all the time, and naturally, increased weight gain. You see people with low thyroid counts that suffer from depression, and that's all related to low thyroid. Like I said, you would see typically pale, puffy skin, dry skin, and so forth. So given somebody clinically that presents with this, and they can measure low TSH and T3 and T4, combine that with the constant feeling of being cold. That's somebody that could potentially be present with hypothyroidism. I've seen this typically used before, where you may have people that come in and say, well, the reason I have this weight gain is a slow metabolism. I've got hypothyroidism. And they can go to a doctor and they can measure your TSH, T3, and T4 and say it's normal. Until you keep trying to find somebody that will eventually say, yeah, sure, it's hypothyroidism. But one of the drugs that they can give for people that can't produce enough T3 and T4 is a drug called levothyroxine, also known as Synthroid. Give them Synthroid and watch their metabolism come back to normal. They stop feeling cold, their metabolism comes back up, their heart rate goes back to normal, the symptoms of depression start to go back down. Those are people that have hypothyroidism because their thyroid won't produce it. Yes?
So TSH in both is low,
Mm-hmm.
in hyper and hypo, but the difference is the T3, T4 is higher in hyper versus hypo.
Yeah, yeah, exactly that. So in that entire negative feedback, when you have T3 and T4, and I know it sounds counterintuitive because here you have low T3 and T4. In hyperthyroidism, you have high T3 and T4. That's all it comes down to, is the amount of T3 and T4, because that is what the thyroid produces. It's the negative feedback mechanism that comes back in that cannot limit it. In hypothyroidism, low TSH results in low T3, T4. Thyroid can't keep up and produce enough T3 and T4, so you constantly have TRH being secreted to stimulate our thyrotropes and so forth. And that was hypothyroidism. In hyperthyroidism, especially Graves' disease, this is where, in hyperthyroidism, when I'm talking about Graves' disease, this is just an example of hyperthyroidism, where your thyroid is constantly making T3-4 without that negative feedback regulation. Okay. Well, let me rephrase that. Negative feedback still works, but you're getting an extra stimulation from your own antibodies.
And then for the goiter, the T3 and T4 are not able to shut down the negative feedback.
On the thyroid?
Yeah.
No, because the thyroid is making T3 and T4. It needs thyroid stimulating hormone in order to make T3, T4. So let's limit the production of T3 and of thyroid stimulating hormone by turning it off in the hypothalamus, which will in turn turn off the anterior pituitary. And Synthroid actually is a wonderful drug for those with thyroidism, any hypothyroidism. Typically what they would do in these cases is they can start off with low amounts of Synthroid, and then they can just titrate upwards. Let's give them a small dose of Synthroid. Let's up the dose a little bit, watch to see if we can start to see a reduction. Keep measuring TSH and thyroid hormones, and they can bring it back up. And there's numerous other diseases that also look at thyroid metabolism. There's another one called Hashimoto's. And Hashimoto's disease comes in, it's Hashimoto thyroiditis or something like that, that comes in and attacks the thyroid. And it starts attacking your own follicular cells, which will limit the production of T3 and T4. So people, Graves' disease is where an antibody comes in and mimics TSH. Okay? Hashimoto's is a disease that comes in and destroys the thyroid. It literally will destroy the cells that make T3 and T4. So typically you would see somebody with Hashimoto's, they have an enlarged goiter, they have an enlarged thyroid at first, and then as your own immune system comes in and starts breaking it down, then you're gonna have to rely on getting exogenous T3, T4, basically your Synthroid. And as long as they can just feed you enough Synthroid, they can still maintain proper metabolic function. you're just having to get it from an outside source. It's very similar to type 1 diabetes, where your own immune system starts attacking the pancreas and you're not making enough insulin. Now, the thing is with insulin, insulin has to get injected into. It's the only oral, we can't take insulin orally because our own digestive system would break it down. Now, Synthroid, T3 and T4, are lipid soluble. So you can eat it and it'll make its way into your circulatory system just fine. So that's the route of an administration of a drug, is typically looking at whether your own GI tract will break down that drug itself. If I were to take a drug that is protein-based, our own peptides in the stomach will just start to digest it, and it wouldn't work. What other questions do we have about metabolism? Let's look at calcium regulation. So calcium regulation, as I mentioned earlier, is, the follicular cells I mentioned are involved in the production of T3, T4. Now the parafollicular cells, again, the cells surrounding the follicular cells, we've got these parafollicular cells that are involved in regulation of calcium. And so the hormone that's involved is called calcitonin, or thyrocalcitonin, simply because calcitonin is still produced by the thyroid, but for the purposes of regulating regulating calcium levels. Calcitonin is secreted by these parafollicular cells when calcium is high in the blood. So this is our way for calcitonin to bring calcium levels down. Now the question is, where do you think we store most of our calcium?
The bones.
In the bones. So calcitonin, as well as the other hormone that I'll talk about that will raise calcium levels up, will be working on bone to tap into those resources. We can get it from bone, but we also can get it from the diet, and we can get rid of excess calcium through storing it into the bone and so forth. I'll explain that. We've got a lot of slides that will go over that. So looking at this, calcitonin, again, the stimulus for calcitonin release is high blood calcium with the purpose of lowering blood calcium. And a way to remember calcitonin is, I know this is a little corny, but calcitone it down. Sounds really silly, but you know what? Years later, I remember it. So this reduces the amount of calcium. We know that something that starts off high will start to reduce it. And what we can do with lowering blood calcium is to inhibit the release of calcium from the bone itself. So with that, we have to look at a term of osteoclast along with osteoblast, with which the next slide will discuss the difference between the two. So you're going to see that increased calcitonin due to high blood calcium will come in and negatively inhibit the production of parathyroid hormone. So what we can say with these two is that calcitonin and parathyroid, which I'll just write PTH, have an antagonistic relationship against each other. Calcitonin will bring down calcium. PTH, parathyroid hormone, will increase the amount of calcium. And again, to keep calcium levels normal. So not only is calcium going to be involved in the building up of bone, but it's also going to be involved in the release of neurotransmitters. We're going to see it heavily involved in the contraction of muscles. So we need to ensure that we have enough calcium, whether we can tap into our bone or we can extract it from our diet. So this is a medical video that was put together. The term with osteoblasts. Osteoblasts are cells that build bone, utilizing calcium. Osteoclasts destroy bone. And this video, while it may not necessarily really lend anything academic, still looks really cool. And I know there's people that get paid a lot of money to create these things. There's graphic artists that put together these videos because pharmaceutical companies will pay lots of money for people that can put together some fancy video that you can walk into and they'll show this drug working, and they've got, you'll see it, you'll see how it works. I don't think there is any sound. Oh yeah, there is. Of course, they gotta have some like epic
Bone
music.
is a dynamic tissue that is continually being built, broken down, and rebuilt in a process called bone remodeling. Bone tissue is broken down and resorbed by multinucleated cells known as osteoclasts. These cells are derived from monocytes which originate within bone marrow. Osteoclasts play an important role in liberating minerals and other molecules stored within the bone matrix. Bone tissue serves as a repository for vital minerals including calcium phosphate and various biologically active molecules, such as growth factors. The release of calcium from the bone can play a role in maintaining its homeostasis within the body. The cells responsible for building new bone tissue are known as osteoblasts. Osteoblasts are thought to be derived from cells found to be associated with blood vessels. Once active, they start to produce the organic component of bone, osteoid, which is predominantly made
Amgen
of
that created this,
collagen.
or at least bought it.
Minerals start to crystallize around the collagen scaffold to form hydroxyapatite, the major inorganic constituent of bone, which contains calcium phosphate. Bone mineral density, or BMD, can be used to estimate the strength of bone and to assess the risk of fracture. As osteoblasts form new bone tissue, many become embedded within the matrix and differentiate into osteocytes. The structure, composition, and cellular processes that occur within bone allow it to simultaneously serve as a calcium reservoir, while providing structural support for the vital organs and for locomotion.
That is the effect of osteoblasts and osteoclasts in terms of our calcium storage. So now, as I mentioned, our parafolliculars are producing calcitonin. Let's take a look at the parathyroid glands, which are these nodules right behind the thyroid. There's these 4 nodules right on the posterior side. You can see them on each lobe, 2 on each lobe on the very back. And our parathyroid hormones, are responsible for increasing the amount of calcium. So their stimulus is low levels of calcium. If you've got low calcium in your blood, your parathyroid hormones are going to be able to increase the amount of calcium from 2 different areas. Number 1, our GI tract. How much calcium do we absorb from our food? And really where a good chunk of that calcium comes from is how much can we tap into our own bone resources. So in this case, you're going to see where parathyroid hormone releases or increases the amount of calcium, calcitonin reduces the amount of calcium. You see how all of these work hand in hand. Here you can see on the next slide over, again, our GI tract as well as our bone, for all the purposes of regulating the amount of calcium. We want to make sure we get enough calcium. And I believe the amount of calcium we need is 10 milligrams per deciliter. Don't worry about it, you don't have to memorize it. I might actually be off. That's okay. The other source of where we can get rid of, well, our GI tract is our small intestine. We can absorb calcium through our diet. We can eliminate calcium through our feces, as well as our kidneys. We can regulate our minerals in our kidneys through urination. So looking at this, you'll see with excess calcium, we store that in our bone through osteoblasts. Just like that video described, those osteoblasts will come in and start to layer calcium into the bone itself. We'll combine that with these hydroxyapatite crystals and layer and layer bone right up on top. Calcium resorption is also known as leaching. At times when calcium levels are low, we can pull calcium from the bone in order to raise blood calcium. So that's one way of doing it. The other way of doing it is extracting calcium from our diet. So anytime we eat calcium-rich foods, we can absorb it if we need it into the blood, or we can eliminate calcium back out the same pathway, as well as the kidneys. The next thing I want to mention this next slide really just does exactly what I described. Oh, I was right, 10 milligrams per deciliter of blood, calcium homeostasis. You can see again that sort of teeter-totter that I mentioned earlier. And any imbalance of such will result in the effects of both calcitonin as well as parathyroid hormone to maintain it within 10 milligrams. So at times when we have high calcium, you'll see calcitonin will allow our calcium deposition onto the bone. When we see decreasing levels, you'll see your parathyroid glands producing parathyroid hormone to raise calcium levels back up through our osteoclast. That talks about what's taking place in bone. Let's take a look again at the pathway. This pathway, again, just another way of looking at it. High calcium is going to get your calcitonin. Calcitonin will decrease the amount of calcium. Low levels of calcium will stimulate your parathyroids to raise calcium back up. So now you see how that antagonistic relationship. The one thing I also want to bring up is the effect of calcitriol. So another thing that gets involved as well. So PTH, when we need to raise calcium levels, the kidneys will secrete another hormone called calcitriol. What exactly is calcitriol? Calcitriol is an active form of vitamin D. Why is that important? Is that calcitriol results in increased calcium absorption in the gut. I'm going to draw this back and in this slide is where calcitriol comes in. So with low calcium results in the kidneys secreting calcitriol. And it is an active form, like I mentioned, active form of vitamin D. So you may have heard, and especially if you look at milk, milk can be fortified with vitamin D. So those that take, if you've ever, especially women around menopause age, are at risk for osteoporosis. And they'll tell you, if you need to increase your calcium, they'll tell you, take in extra leafy vegetables, take in milk to increase your calcium. But what they'll also do is tell you, make sure you take vitamin D with it. Because vitamin D will increase that absorption from your food. You can take calcium in, but if we don't have vitamin D, we don't minimize, we don't maximize how much we can absorb from our diet. So vitamin D comes in from, again, you can take a vitamin for it, or you can get a little sun with it. But typically, vitamin D and calcium, whenever you look at any supplements for calcium, will also include vitamin D with it. All right. Let's take a look at, or rather, what questions do we have about calcium regulation? Yes?
So kidneys could get rid of it, as well as the small intestine, and then osteoclast, which will absorb it back into the blood, whether will that still come out the kidneys or the small intestine, or?
Only in terms of excess. You have to think about it in terms of what is excess. Because from this slide, what happens is if calcium levels are low, osteoclast will pull it from the bone.
Yeah, that's what I'm saying.
Yeah.
Well, how does it get rid of it? Would it go out through the kidneys and then get filtered out through urine just the same way as it will go through the?
Oh, they happen all concurrently. So not only are we tapping into bone, but we also work with our kidneys. So think about it in extreme cases where we need to get rid of calcium. Typically what would happen is the osteoblasts will start storing that calcium, but if calcium levels are still high, we can still get rid of it through the kidneys as well as our gut. So both of those work hand in hand.
As well as osteoclasts.
Osteoclasts will come in and pull from the bone. Exactly. They'll pull from the bone, and they'll limit the amount of calcium eliminated through urine and through feces. So just different mechanisms that come into play. How the body prioritizes it, I don't know. But nonetheless, they're just ways of being able to regulate our calcium levels, one way or another. So the adrenals. The adrenals, we're going to start to take a look at two different regions. We have the adrenal cortex and we have the adrenal medulla. And we'll talk about what the cortex is. If I were to draw what the adrenals look like, we have an area on the inside called the medulla, and the cortex will be the outer layer. So cortex being like the cerebral cortex, the outer layer. Medulla being like the medulla oblongata, which is inside. And these two different regions are going to create two different types of hormones. And those hormones you can see, if you look at the term cortisol, it kind of has the term cortex in it. So we're going to be looking at different cortical steroids. The inside, the adrenal medulla, again, this is an extension of our autonomic nervous system. When we talked about the sympathetic pathways, we have which I'll show you on the next slide over, we have sympathetic preganglion neurons. That will come in and target, they'll bypass the sympathetic trunk ganglion, and they will travel to the adrenal medulla. So these preganglion neurons, remember, what I mentioned in our peripheral nervous system is that the preganglion neurons come in and terminate specifically in the adrenal medulla for the purposes of producing our catecholamines, norepinephrine and epinephrine. So inside that adrenal medulla, we'll find neurosecretory cells. These are modified postganglion neurons that have merged their function with endocrine cells. So this is going to talk about the production of our catecholamines, which will be, like I said, epinephrine that will drive the sympathetic response. The adrenals being the hats on top of the kidneys. The adrenal cortex, again, being the outside, being the bulk of the adrenals. You'll see three different regions that you're going to be able to see in the adrenal cortex. So we can divide this up. An outer layer, a middle layer, and an inner layer. Middle layer being right in between. So these three different areas of the adrenal cortex is going to secrete three different types of hormones. Like I mentioned earlier, these are all going to be cortisol type hormones, steroids. We'll be able to see three different types. The mineral corticoids are the ones that are produced on the outside. So these will be the outside. So outside, outer will be mineral, the inner, the middle, and then the inner. Middle being our glucocorticoids, and then our inner are going to be androgens. And these are going to be our masculine-like type hormones. So these three fundamentally different zones are going to create these three types of hormones. Mineralocorticoids are all related to the regulation of minerals. And we'll be able to see which minerals we're talking about, specifically sodium and potassium. So sodium and potassium are going to be the big things on it. Why are these important? Well, you see these are going to drive the membrane potential. We want to ensure that we have the right amount of sodium and the right amount of potassium in the extracellular fluid. So it's prudent that our own system can come in and regulate those levels. We don't want too much of it, we don't want too little of it, because that will specifically affect the membrane potential of our nerves. We want to make sure that that's functioning properly. Not only that, sodium and potassium are going to, which we have plenty of, is going to affect also the osmotic pressure. These are all going to be tied in to osmolarity. How much solutes are dissolved in the extracellular fluid. So that tonicity is going to drive whether the cell is going to be functioning or not. So I'll talk about that. Aldosterone is going to be the key pathway that we will get at on the next slide over. Now glucocorticoids are responsible for, if you see the term gluco, it's all going to be related to glucose. How are we able to tap into glucose to be able to bring about glucose and utilize it as a metabolic substrate? And so we'll talk about the effects of stress, a stress hormone called cortisol. Cortisol that's going to be heavily involved in being able to stimulate the production of glucose. And then lastly, we'll take a look at our weak androgens. We won't even really talk much about weak androgens, but these are masculinizing sex hormones. Testosterone being the biggest one in men, but women also have the same androgens. These are produced by the adrenal cortex. And one of the common ones on here is one called DHEA, which I can't remember what this is used for. Typically used for children for the formation of nerves, but these also play a role in promoting libido in women. This is a big one. So for the adrenals, this is actually a significant source of estrogen in postmenopausal women. So with the decreasing function of the production of estrogen, we'll see this is where it comes into place. All right, so let's hone in our focus on our mineralocorticoids in our purposes of regulation of sodium and potassium. This image right here can scare people, because it should. Looking at RAS, as I mentioned earlier, looking at osmolarity is all related to the amount of solute over the amount of solvent. And our osmolarity, this entire purpose is to make sure that we can still maintain proper blood pressure and maintaining amount of fluid. And we know solvent, in this case, isn't just any regular solvent, it's water. So what we want to do in terms of the solutes is to ensure a good amount of sodium retention, while decreasing or maintaining normal levels of potassium. Remember what I said earlier, in our earlier slide, is we want high sodium on the outside, we want low potassium on the outside as well. And that's going to maintain the driving force for our action potentials that will take place, our graded potentials and action potentials. So with that, we want to make sure that these are working together. So what we're going to be able to take a look at is the renin, angiotensin, aldosterone system, and that's all described for you on the next slide over. So don't worry about having to write all this stuff down. You'll be able to see it described for you on the next slide. The renin, angiotensin, aldosterone system. And this is kind of one of the funny ones, because you see all these different organs that are involved in trying to maintain blood pressure. And I'll break it all down for you. The first thing is that we have to look in this process is to look at what the starting point is, what stimulates this system, and what the end product is. Our stimulus, in this case, is dehydration, low sodium, or hemorrhage, a loss of blood. So this takes place when we see low levels of H2O or low levels of sodium. And the only way you can get this to take place is to not have enough water in your system, or you lose blood, or any system that takes place. Now, the decrease in blood volume or the decrease in blood pressure, think about when you lose a good amount of blood, you're losing both. And so looking at the area that detects blood pressure that's involved in the RAS system is the juxtaglomerular cells. It's something we'll talk about in our urinary lecture, are called our JG cells. They have baroreceptors that detect the amount of blood flowing through that area. Because as you know, the kidneys are responsible for blood filtering. And as blood flows through, it can determine the amount of output. It's saying, this is how much blood is flowing through. And if there's not enough, what it's going to do, it's going to release an enzyme called renin. And renin is going to come in and start floating through the circulatory system. Now the liver produces a protein, which is not an enzyme, a protein called angiotensinogen. And it's one of the proteins that's constantly floating around in the blood that the liver makes. And angiotensinogen, that's moving its way through the circulatory system, once renin gets secreted into the circulatory system, renin comes in and cleaves angiotensinogen. It finds this protein, it looks for a key amino acid sequence, and it cleaves it. So now it's going to turn this huge angiotensinogen molecule into something called angiotensin 1. That's our end product after renin cleaves it. Angiotensin 1 is now still floating through the circulatory system, and eventually it's going to make its way into the lungs. And I have no idea why it's built this way, but the enzyme that's going to convert angiotensin 1 and cleave off 2 amino acids from it is located in the lungs itself. This is called angiotensin converting enzyme. Angiotensin converting enzyme turns angiotensin 1 into angiotensin 2. Angiotensin 2 then makes its way back, and it's going to make its way all the way back to the adrenals, close to where we started in the kidneys. And once it makes its way into the adrenals, it will stimulate the production of the next hormone called aldosterone. So what does aldosterone do? It comes in and increases. It does the exact opposite of what we needed. We had low H2O and low sodium. So it's going to then retain our salt, retain sodium, retain water, and then also eliminate excess potassium, and as well as hydrogen ions. So in the end, we wanted to do exactly that. Raise sodium, decrease potassium, and raise water to bring it back up. To make sure that we're still maintaining isotonicity. Increase your solute and increase your water. Now angiotensin 2, this is the other pathway that I need to describe. Angiotensin 2 comes in and also has a direct effect on the arteries, where it's going to cause vasoconstriction. Now take a bunch of whatever remaining blood is in the arteries and squeeze them. And what that's going to do, it's going to increase blood pressure. So therefore blood pressure raises back up. Combine that with increased water retention, increased salt retention, and now we increase blood volume. So what started off as a decrease in blood, in water, a decrease in sodium, results back in the exact opposite of it. So it is a long pathway, but it's a necessary pathway because that's what the kidneys are attuned to doing. What questions do we have about that? Again, complicated pathway, just kind of follow where it goes. And again, I described that all for you on the next slide over.
Isn't there similar to vasopressin, like the same concept?
I'm glad you brought that up. So vasopressin, ADH, antidiuretic hormone that's produced by the posterior pituitary, is all related to water. That ADH, as an antidiuretic hormone, wants to specifically retain water in the kidneys. Okay? That only looks at water, and where ADH, and this will make much more sense when we get into your urinary lecture, ADH wants to play a role directly on the collecting ducts that are supposed to extract water into the urine. And that's where ADH comes in and blocks it and says, nope, we're going to save it and we're going to make sure it stays in our circulatory system. This, in the aldosterone system, renin-angiotensin-aldosterone system, this is not only conserving water, but it's conserving our essential electrolytes as well. So yes, they work hand in hand, but they work in different areas. This specifically starts off in the kidneys, works in the adrenals to produce aldosterone. At the same time, if you're also losing water, you also want to recruit ADH as well. But keep in mind that if you're retaining just water, that's not going to affect your sodium. Think about when you've lost blood and now you're trying to take in a bunch of water. What you're going to end up doing is you're going to make your blood more hypotonic. You're just taking in water. That's going to reduce the amount of solute in the amount of H2O. So if I have my solute, as I mentioned here, and all I do is raise H2O through ADH, now I affect the osmolarity. My cells won't work as well. In fact, what's going to happen is water is going to leave the cells, which is not what we want to do. We want to raise those ions back up. So in this system, in this slide over, I want to talk about, and this I know is kind of an old looking image, but what it does really well is you see angiotensinogen, again produced by the liver. This is a rather huge protein, about 400 amino acids long. Renin comes in and cleaves off these two leucines together. So what you end up is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 amino acids long. That's the sequence for angiotensin 1. So you notice how this is the same right up to this point. Cleave off all this, and this is angiotensin 1. Angiotensin converting enzyme produced in the lungs comes in and just cleaves in between these two right here. So cleave off that area, and now you get angiotensin 2, which is only 8 amino acids long. And technically there is an angiotensin 3, which I didn't cover, and all that does is it cleaves off ASP. And now you've got a 7-digit, or 7 amino acid long. And that's going to come in, and there are receptors in the adrenal cortex that will take in angiotensin 2 and angiotensin 3 to produce aldosterone. So looking at this whole process, you'll see that why is this so important? This is all related to the regulation of blood pressure. What we see as a decrease in blood pressure results in the increase in blood pressure. Now, why is this so important? It's because this is a form of hypertension. This whole thing is all related to a type of hypertension that is prominent, especially in not just African American populations, but African populations. The big thing that is an issue is what's called renal hypertension. There's a set point in the kidneys that say this is the proper amount of blood that should be flowing through the kidneys. Now, as blood flows through the kidneys, if the set point is off on the juxtaglomerular cells, and it just says, well, the amount of blood that's flowing in is too low, when it actually is just fine, what that's going to end up doing is going to start secreting renin that will go through this whole system, converting angiotensinogen to angiotensin 1, and then getting converted from, by this ACE enzyme to angiotensin 2, which effectively will start increasing blood pressure and retention of water. So if it's normal in the kidneys, but it's detected as low, that will raise blood pressure. So in this form of renal hypertension, what you can do to limit the production of aldosterone and angiotensin II is come in and find some inhibitors of enzymes along the way. One of them being, oh, here's our ACE enzyme. Let's get something called an ACE inhibitor that will limit the production of angiotensin II. So I talked about a drug, beta blocker. I talked about that, when was that? That was last week. Beta blocker specifically blocks the adrenergic receptors. Okay? Those block the adrenergic receptors from receiving epinephrine. So in that process, those adrenergic receptors are blocked and therefore will limit the heart contraction from taking place. Okay? So that reduces the heart rate, and therefore if you reduce the heart rate, will reduce blood pressure. This is another mechanism where you're working on the endocrine pathways. You're specifically limiting the function of the enzyme in the lung. Okay? That's not the only pathway. There are other pathways involved, other hypertensive drugs. There's beta blockers, as I mentioned, which works on the autonomic pathways. We have aldosterone receptor inhibitors. Well, one common drug on here is aldactone, also known as spironolactone. And that specifically works in blocking aldosterone. Okay? So that blocks it right back in the kidneys. Other drugs involve ACE inhibitors. Any drugs that end in PRIL, captopril. You'll see other drugs like lisinopril. Lisinopril is another one. Did I hear another one? Okay. Enalapril. These types of drugs will inhibit those enzymes. The other one is angiotensin II receptor inhibitors. CoZar is a big one. So going back to where angiotensin II receptors are, on the arterioles as well as the kidneys. Block angiotensin II onto binding onto the adrenal cortex or the arterioles will limit the production of aldosterone. So numerous pathways that have been discovered. And in that entire pathway, you can see when they were discovered, when they can actually block those out. So renin inhibitors being some of the early ones. Let's stop it earlier on in the process, directly from the kidneys. Here you see ACE inhibitors that have been employed since the 1980s. They discovered that drug pathway. They can see peripheral sympatholytic ganglion blockers. These are things that end up blocking the peripheral nervous pathways to limit the presence of hypertension. All different types of channels or receptors that they're blocking. And they all effectively work the same way. If they notice that CoZar doesn't work, maybe they can try aldactone. And of course, which clinical drugs they try first, I don't know. But they know that there's numerous pathways that can come in just to stop the production of aldosterone and angiotensin II. And that whole effect. Can we take a break? Yeah. Okay. It is 8:25. You want to take a